How's everyone? Cool. I'm Tom. Nice to meet you. My name's Tom Gallacher at Tom GK. I work at Yield as well, and I am a senior software engineer, and I program primarily in Node, and I love performance, and that is what my talk is about today. Performance in Node, exclusively Node.js, and it kind of tends towards Docker as well. I'm going to touch a couple of things about Docker in this presentation, but I won't explain them because they will be explained later in Andy or Luke's talk. So I'm going to skip over them, and hopefully they'll go into more detail about that. So why do we need performance monitoring, or not even monitoring actually? Why we want to kind of dive into looking at an application of some kind, just because we're inquisitive, because we want to see what makes it tick and how we can kind of get those extra couple of milliseconds of response time from our requests. So one of the problems I've had in the past is building a HTTP API and using MongoDB as a backend, as kind of my database. When you're querying large data sets in Node, the data sets take a while to actually parse, and you can kind of actually get some big latency coming back from MongoDB. And that's not necessarily because the database is slow. It can be because your application can't retrieve it fast enough. So MongoDB stores its data in something called BSON or Bison, which is basically binary JSON. So it's kind of like just a ridiculously compact JSON representation, which is not readable by anyone. Now, JavaScript and Node.js, basically to understand this, can't kind of in memory take this Bison object and kind of represent it as a JSON object. It needs to be deserialized into JSON to be used by our application, and we have no idea what that is until that's happened. And writing our own parsers in JavaScript or whatever it can be slow, because we have to go byte by byte, collecting, basically saying, is this a string, is this a date object, and then building up kind of like your JSON representation. So, and that's slow, in kind of like milliseconds kind of areas. And the bigger documents you have, the slower it goes. So we're going to profile this Bison module, which is used by the MongoDB driver in Node.js, to see kind of like where the time in this parsing is actually, where it's actually spending most of its time. And so how do we do that? So we can use some tooling, these kind of like just large kind of overviews. So flame graphs. Flame graphs are kind of like graphs which show you where most of your execution time is spent. So the wider the graph and the deeper the color, I'll show you some examples in a second, basically means that it's being called more often and it's taking longer and longer. We can use the Chrome CPU inspector. So in Google Chrome, we can kind of like pull up the profiling tab. Because it's JavaScript, we can just open up a web browser and load up this file, which will generate in a second. We can use the Chrome tracing, which is kind of like another thing in Google Chrome, which is kind of hidden behind the back doors, which allows us to explore this data in more depth. And dtrust and strace, which are kind of Solaris and Linux tools for actually looking at what the kernel is doing when our application is actually being interpreted by the operating system, which is like on a totally different level. But so to start off with, we can do it in Linux and Docker. So we can basically do a run, mount a directory inside of Docker container, basically run our application, call bash on it, and then basically use the Linux perf command to record the number of cycles that this application is basically is taking. And because we're passing this hyphen perf basic prof to the node command, which is just out there, we actually get a kind of a description file out from Node itself, which will basically give us it will give us a massive deep analysis of what our actual Node application is doing. So if we have a look at that, we can also do the same in Darwin and Solaris, but instead of using the perf command, which is kind of that one, perf record -e, we use a dtrace script. So because I'm running on Mac, both of them was going to work on Docker and on Mac OS X, but I'm going to just do it on the Mac side, just so I get nice paths of where my files are actually being executed. So let's have a look. So I'm going to jump out into the terminal now. Is she going to let me? Oh, no. 1 second. Good job this wasn't running on Linux. Don't need that. Cool. Right. I preempted this happening. Right. Don't you love computers?
What's wrong?
I don't know, it's kind of just my slides are working, but let's try and quit on them. Die. Let's save that. Part 1. FL. Cool. Part 2. Let's hope all my tabs are still there. They are, great. Keynote. What was that done? Hello, welcome back. Let's pretend that didn't happen. So now we're going to basically run this profile script. So we're going to kind of actually attach a some profiling at the kind of kernel level. In Linux, this will be done using the magical tool called perf, and in Solaris on your Mac, you're going to use dtrace. So on the Mac, I'll show you, you would use this profile underscore 1ms.d. So this is it's basically a description in the programming language called D. The kernel, which is the Mac OS X system, has this thing called dtrace probes. So these are kind of like kernel probes which kind of sit inside of all your different applications. They're like minimal latency, and you can kind of toggle them on and read from these probes when you want to, and you basically describe in these scripts when you want to activate those. And the nice thing about Node.js itself is that developers have actually basically had their own custom probes compiled into the kind of V8 interpreter and kind of the bindings as well. So we can actually get Node.js performance information by using dtrace or perf on Linux, so we can get that granularity. So we would basically run profile D. It has to run in sudo because basically it requires deep level kernel switches, and you need to be a super user to be able to do that. And you basically run the command node perf basic prof, so that will give us the data that we want. And this is going to be our benchmark here. Now our benchmark is just a, oops, come back here. So this is just our benchmark here. Basically what it's doing is it's building up this object here. This object is then going to be serialized into Python, which is going to be basically it's just a binary string which would be stored in the kind of a Node.js buffer. We then serialize that, and we do that a certain number of times, and then we are deserializing it back to JSON. So we're going from a JSON object to a buffer of binary data, and then back to this JSON object. So this was what would happen if you were, say, if you were writing something to MongoDB in your Node.js driver. You would have a JSON object. You take that to Bison. You then send it. It stores it in the database. You get it back, and then you present it as JSON again. So as we run that, we will. Well, I won't run it right now, but we have an output. So that is basically going to output this profile d.output.text. Now this, as you can see, is a very large file, and it basically is a very unreadable mess of output. But what you can actually see here is some metadata on the line where my cursor is, and basically the kind of core stack inside of V8 itself, the underpinning engine of JavaScript, and kind of what functions are being called inside of that. And you would also see some of your own functions in there as well.
You can only not see them in OSX.
Okay, right, yeah. If you...
Because OSX doesn't implement something called user stack trace helpers or something.
Yes.
That should translate those to actual function names.
Yeah, so yeah, these hashes here, the ones where my cursors are, they are actually internal functions that are being called, but because we don't have the visibility on Mac OS X because it's proprietary. Well, you saw what happened when it crashed. But that this you can basically generate this on Linux as well by using the perf command. So you do perf record -e blah 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 blah, and you get the same output as well. What you can do then at this point, because this is kind of a Node.js format, we kind of want to make that into a format which we can use everywhere, if you were. Google Chrome, basically in the Google Chrome tools, have this has this profiling, right? So you can do front-end JavaScript. You can start, record your profiling, stop it, and then kind of see where your time is taking. But we can exploit this and use this in Node.js as well by just creating the file which Google Chrome takes, because it's JavaScript, it's functions, we have line numbers, etc. So what we do is basically send that to CPU profile, CPU profiler,
Profile file.
Exactly, and basically we'll pipe that out, and this will convert it into this .cpu profile file. This is a JSON description, basically, of your application. So at the bottom here you can see just timings, so this is kind of just so it knows where to put a load of stuff, and if we look at the top of it we can see that it's just kind of a definition, the name, title, head, and it kind of is a massive hierarchical JSON object which describes what your application is doing. Now that's not really easy to see what we're doing, so we open up Google Chrome, and if I am in the right place, which I'm not, here, you can open up it inside of Google Chrome, and you basically get presented with this. This is what's happening inside our Node.js application. You can see it there. I'll make it a little bit bigger. Like right at the start here. So this is the first second of execution. So we have line 1 second, 2 seconds, 3 seconds. So this is what's happening in line. So you can see that Node calls load environment, startup, it does a load of module stuff. Like that's where your requiring happens, and yada yada yada. So if we have a look at this point onwards, so we can kind of see, oops, come back here, that we can see that there is actually bison.serialization happening, and we can see how long it took itself, the time it took in total, the file that is actually processing this, and that also includes the line number, and kind of like the aggregated time. This gives just a really good look into what our application is doing, but as you can see there's so much data here that it's almost impossible to make sense of it without spending hours and hours and looking through each of these little nodes and going, oh yeah, this casting a value to a string in V8 In this case, it took around under a millisecond. And you can kind of go, this doesn't really matter. But okay, calculate element took a total of 7.2 milliseconds over a couple of executions. So that's really interesting. The next bit is that now we've got this .cpu profile file, we can convert it into a tracing file. Now this is just another thing that's available in Google Chrome. You can access it by going Chrome/tracing. This is just kind of just a hidden feature underneath, and you can run this on your client-side application as well. But we're going to convert our .cpu file into a tracing JSON definition. So we basically would just tracify, trace viewify our CPU profile into this trace internals of JSON. So we can now switch to this tab and switch to this tab. There we go. So this is again roughly the same thing, but with a lot more granularity. So you can see here that we can basically look at kind of a slice of our execution, so we can kind of see what's happening at this point in time. So you can kind of, for example, I can select a little bit here, and then press M, and what I can see is that our benchmarks.js is being called, and that is taking 2.4 seconds, or 24 seconds. So that is basically the duration of everything, but that's not how long that actual function takes. It's the kind of how long that function takes, but it's not necessarily the slowest thing if you're looking to optimize it. The reason being is because that function could only be calling another function to do something, and you're looking at ways to optimize your code to actually be as fast as possible, and focusing on the big functions that only call other functions, there's not much to do there. So instead of looking at kind of how long it takes in duration of these function calls, we can actually look at how often things get called.
Can you zoom in a bit, Tom?
Oh, yeah, sorry. Whoa. Okay. So coming back here, so this is kind of like the duration of this Bison function being called. We can actually look at this here. So because this is, I ran it on my Mac, it has the full path, so I should be able to just open that up in Vim, and it's a large file. You can see that it's that calculate element function being called. Yep, so you calculate element. Now you can see here as well that it has a tilde and a star. That is something that we can go into in a little bit, but to go back to here, it's actually what the V8 itself is optimizing it. So there's a way that V8 optimizes functions itself, because it compiles them. Having nothing means it's compiled. Having a tilde means it's optimizable, so if it gets called enough in the future, V8's going to go, alright, I'm going to try and optimize you now, because it's being called a lot, and obviously it can try and hint to make things faster. And then the star means it's optimized, and V8 has basically said, alright, we made this as fast as we can. So that kind of is another hint we can kind of use when we're kind of looking at what functions to improve the speed of. And when you've got summed together, so this here, it means it was optimizable, and then it was optimized, and then it's gone back to being not optimized again. So it means that it's actually, as you would call, a de-opt. V8 basically would have gone, I'm going to optimize this, and that takes a bit of time. Cool, it's optimized, and now a different code path is optimized it for a integer equals an integer. So it can say, it makes an assumption to say that every comparison is an integer and an integer, and that can be really fast. But then as soon as because of polymorphism, as soon as you send a string in there, V8 will be like, whoa, this is not what I expected, and it will then chuck it into this kind of de-optimization state, and it will then kind of do that a couple of times, and that can take it basically choose the performance of your application. But going back to kind of like looking at the occurrences of these calls, we can see that that call itself, that function, is being called 25 times, and it's taking 40 milliseconds each time it gets called. What that means is that it's 40 times 25 of the overall execution time is in that function. So that basically points to me to say, have a look at that, see if there's anything we can kind of improve in here. And as you can see in here, it's a massive switch statement where it's going, oh, is it a string? Is it a number? Is it undefined? And that kind of hints at we get a certain value, so it optimizes it for like a string, and it kind of ignores like everything under here, and then a new value comes in, and then it can't optimize for that, and it kind of slows down, etc. So that's another thing we can kind of look for. And I mean, you can I spend hours just looking through this, trying to find the kind of couple of milliseconds of improvement. Now another view, snapshot into kind of what our application is doing, which is a lot more simpler to look at, is a flame graph. So we can do the same. We can call flame graph if I pipe it into it. Just pass it into flame graph. That'll create an SVG.
Those are all Node modules.
These are all Node modules. I'll put them. Well, I won't put them up at the end, but we'll put them so you can kind of see where they are.
Cool.
But it basically just inputs data and then does stuff to it and then outputs it. But that creates an SVG, which would look like this. So you can see it's kind of an interactive SVG, and it's the same thing. We got a node start, node environment, some function calls, and you see that the darker the color, the more times that function's been called. So you can see that bison.serialize has been called a lot of times because it's a lot darker. But you can see that actually it's not actually using that much time. Whereas calculate element, that function again, is actually taking quite a lot of time here. So we can actually zoom in and kind of like looking deeper and deeper into the call stack and see that basically calculate element calls these functions, which so it does something with doing stuff with the buffer itself, because it takes it from a Node.js buffer and tries to move it into a string. You see here, this is parsing something into UTF-8. So that's where I would look at the slowness of the parser, is that it's parsing a lot of strings from binary into UTF-8, and that's quite slow. And you can kind of just look through, and the darker the color, the more interesting it is. So we can kind of have a look at this, and kind of just see the number of samples and kind of like what is actually happening underneath. Extremely explorative kind of view. So you can see in this case we call a function called read C12 string. So this is just going to be a binary. You have a binary string, and we're basically looking for a null terminated byte at the end, and then saying this is a string that we can put into V8. And the way that this application does this is does a while loop for it. So the bigger the string, does a while loop. It's going to be blocking your Node.js application, your response time to go up, blah blah blah. So that's flame graphs, and I mean, with all those tools, you can kind of like make an assumption and hope that it's the right thing to do, and play around with modifying the source code, modifying kind of what you have done, running everything again, and making sure that it actually has made an improvement or it hasn't. And if you can kind of like keep doing that, you can kind of actually visually see, based on these cool graphs, what has changed and where you're actually improving your application performance. So that's pretty much it. I mean, there's a nice documentation here, which is, if you want to go even into more detail, this is just a document which you can kind of look at even more things that come bundled with V8, which will allow you to look at your JavaScript, plotting tick data, which is how often, what happens on each tick of Node.js, the event loop, memory histograms, so you can see how much where you're kind of allocating memory where it's not, tracing, analyzing data. There's just loads of stuff there. And then there's also, if you want to go into a whole different level, you can actually look at what what V8 is actually interpreting your JavaScript as. So this is an example function. Basically, just it's a vector. It's using prototype inheritance. It's got a length function. It's got a loop, etc. And you'd think that's pretty performant. But if you're doing this loads and loads of times, what can happen is that some things can be de-optimized because you're changing the type of data into it. So this is something called IR Hydra 2. So it decompiles your JavaScript into IR code, which is used by the compiler internally, and you can basically break down into kind of almost assembly kind of level JavaScript. So this is still JavaScript, but this is what the actual compiler sees. And what's happening here is that the hidden class underneath of using prototype inheritance is being changed, and the compiler isn't smart enough to fix that. So this tool actually tells you where the deopt is, what the deopt actually means, and kind of like how you could probably fix it, if you can or can't. You can then look at the same as length. You can say, do the same thing here. You can kind of view kind of the graph. That's not very interesting, that one. You can see where your execution's gone through and whether you've hit an if loop or for loop. It will kind of say, right, that's gone down here, this code path jumped back, and then that's a secondary code path that can also happen. Like, as you run your application, this kind of the interpreter will build up a bigger and bigger map of what your application is doing, so it can preempt how to make stuff.
And you can
faster.
just put any JavaScript source code there?
So you have to run Node.js with a lot of different commands.
Oh.
Let's have. I'll show you what those commands are now. So you have to run it with trace hydrogen, which is the underlying second compiler in JavaScript. So there's two compilers, one which is the runtime and one which is the optimizing compiler. And then you trace phases, trace deopt, which is kind of when the compiler goes, can't make this optimized. Code comments, track positions, redirect code traces, assembly, print optcode, and you can do the same with Google Chrome as well. But as soon as you've added that in there, it's going to create a massive file which you can then just load up in the web here and kind of just play around with it and kind of just look through. And it's I've never used it like properly because it's just too crazy, but it's a really interesting thing if you want to micro-optimize your.
And you probably wouldn't want it to run against a full-blown app, probably just against a small sample.
A very, very small sample, because I mean this is what, 39 lines of code, and you have well, you can see what this is all here.
Yeah.
It's so much data that is really difficult to understand. But if you like, as we have done, track down kind of where our bottleneck is, we can kind of take that out, isolate that, run an isolated benchmark against it, and then keep playing around with that until we can get a small enough sample set and a good example of where things are going wrong, that we can use this tool to tell us what's actually happening. But all of this is it depends how deep you want to go. Like the flame graphs is usually enough to kind of see if you are
It's taking more time.
yeah, if stuff's taking longer, and you might just go, oh, actually, let's just change out that module. But if you want to kind of fix it yourself, you can go to this level to play around with it. But so
I'd just like to say one thing about the flame graphs. The first time I saw them, I thought that the horizontal
axis
had some meaning, but it actually doesn't.
no. So if we just look at this, the flame graphs again. Where is it? Sorry for darting around. So yeah, this sideways doesn't mean anything.
Doesn't mean.
It's just a way to show it. I think it.
Just the wider it is, the more time it's spent, regardless of where it is on your